We are now going to do a hybrid proof for the security of the scheme. Now, hybrid proofs have three rules. Rule number one is that there will be a first hybrid, okay, H first, let's say, and the last hybrid, let's say H last. These two should be the two things that need to be indistinguishable. So essentially, in a hybrid proof, our goal is to prove that this first hybrid is indistinguishable from the last hybrid. But instead of doing it at once, we will do it using hybrids. So we will define the second rule that says consider two neighboring hybrids, Hi and Hi plus 1. Distinguishing these two hybrids should mean breaking some underlying scheme, some underlying assumption. Remember, we said hybrid proofs, one of the main uses of them is when some primitive is repeated multiple times. So here we have Gn plus 1 repeated multiple times within Gn plus Pn. Essentially, we will define our hybrids such that the only difference between two neighboring hybrids would be something related to Gn plus 1. Okay? This is our underlying assumption. So if the adversary can distinguish between one of these, we will show that we can distinguish, let's say we can break Gn plus 1. The third rule says there must be polynomially many hybrids. So in some sense, this will mean that we will call our H first as, let's say, H0, and our H last as, let's say, H some, let's say, Pn for some polynomial n. Okay? Let us define our hybrids for this particular proof, and then it will all become more clear. We will define hybrid I as follows for this particular proof. So hybrid I says pick a random value S that is n plus 1 bits. Sorry, n plus I bits. Okay? So pick a random n plus I bit value. Then let me label these with, let's say, levels. So this is the 0th level, first level, second level, third level, etc. So if I run Gn plus 1 once, this corresponds to first level. If I run it twice from the beginning, second level. 3 times from the beginning, third level, etc. So the last level would be Pnth level. So hybrid I says pick some random S that is n plus I bits, and then continue this construction, okay, from level I. So start at level I, okay, and continue there. Let's see what this means for some values of I. Consider H0, the 0th hybrid, the first hybrid essentially. What it would mean is we would be picking S that is how many bits? You see it, n plus I is 0, n bits. And then start at level 0. If I start at level 0, so I have n bits of random value, I start at level 0, do these things. This essentially corresponds to running Gn plus Pn. So pick this S and then run Gn plus Pn using this S as the input. It will give us some random value, let's say R, a pseudo random value R at the end, and the length of this R would be n plus Pn bits. Let's look at HPN. So when I is equal to Pn. What it would mean is pick S that is of length n plus Pn. So I is equal to Pn. According to the hybrid definition, this means we are picking S that is n plus Pn bits. And then continue from level Pn. If I continue this construction from level Pn, there's nothing further to do. Essentially, I can say that my R, that is the output, let's say, would be equal to S. Now, if you consider these hybrid definitions, H0 essentially is picking a random S, running Gn plus n, and then outputting. Okay, so my H0 is in some sense the pseudo-random experiment. What is HPN? HPN is picking a truly random value of the same length as the output of my pseudo-random experiment. So this is my random experiment. Remember, pseudo-random generator definition, security definition says this experiment needs to be indistinguishable, computationally indistinguishable from this experiment. So if I manage to prove this H0 is indistinguishable from this HPN, then I am done. That's the proof I am trying to eventually form. Now let's look at some neighboring hybrids. Consider, for example, H1. What is H1? H1 would mean pick n plus 1 bit random value and then continue this construction from level 1. What was H0? Pick n bit random value and then continue from level 0. So the only difference between H0 and H1 would be at this first step. Hybrid 0 uses Gn plus 1 to perform this first step. Hybrid 1 doesn't use Gn plus 1. It picks these n plus 1 bits completely randomly. So the only difference between hybrid 0 and hybrid 1 is this one use of Gn plus 1. Consider hybrid 2. Hybrid 2 says pick n plus 2 random bits, continue at level 2. So pick n plus 2 random bits, continue from level 2. Between hybrid 1 and hybrid 2, the only difference is running this Gn plus 1 once. So between each Hi and Hi plus 1, the only difference would be we are either running Gn plus 1 more time, or we are starting randomly. So essentially, this difference here would correspond to distinguishing Gn plus 1's pseudo-random output from a random value of the same length. Remember, that's what we wanted to achieve. Distinguishing each neighboring hybrid should correspond to breaking some underlying assumption. The assumption here would be Gn plus 1 is indistinguishable from random. Do we have polynomially many hybrids? Yes, remember our last hybrid is Pn, so we have Pn plus 1 hybrids essentially. Remember, Pn was a polynomial, so we have polynomially many hybrids. We satisfy all three requirements of a hybrid proof if we define our hybrid I as this. Now, the next step would be proving this using a reduction. So this was only, let's say, a starting point for us. Next, we need to prove. What's the theorem we are going to prove? Let's write it first and then we will do the proof soon. The theorem says if this Gn plus 1 is a secure pseudo-random generator, okay, that has n plus 1 bit output, then this new pseudorandom generator we defined, Gn plus Pn, which is essentially this whole construction. Remember, repeating Gn plus 1, Pn many times on the first n bits of the output, taking these extras here. So this construction then will be a secure pseudorandom generator with n plus Pn bit output. So this is the theorem we are going to prove, and in our proof we are going to employ this hybrid definition.